Namaste student. Today we are going to study Science and Technology Part 1, Chapter 1, Gravitation by online presentation presented by Bhujwal sir from Sambhajiraje Vidyasankul, Jatega. Newton's Law of Gravitation. Statement: every particle of matter attracts every other particle with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. The mathematical equation of Newton's law of gravitation is given below. As shown here, F is the gravitational force in between these two objects of mass small m and another object having mass capital M. If the distance in between them is r, then the gravitational force in between these two objects F is given by this equation G m upon r square. Newton's law of gravitation. In the equation, capital G here is called as universal gravitational constant. The value of this gravitational constant is 6.67 into 10 raised to minus 11 Newton per meter square per kilogram square. This value is calculated first by scientist Cavendish, and the value of G is same in the universe. Any object of any masses, any distance between them, value of G is not changed. That means it is a universal constant. G is a constant throughout the universe and it does not depend on the medium between the different masses or any distance between them. Then in this chapter we study the Kepler's law. Scientist Kepler, Johannes Kepler, formulated three different laws about the planetary motion. That means how does planet revolve around the sun. According to Kepler's first law, every planet revolves in an elliptical orbit around the sun, with the sun situated at one of the eclipses. So this is the planet and this is the sun. This planet is revolving along this circular elliptical path as shown in this activity. Look, planet is revolving around the sun in elliptical path. Elliptical means Lambavartul. Okay, this is about the first law. Sun is at one of the focus. Focus means the center of the ellipse. Every ellipse has two centers. So this is the one of the center here. Sun is now at this focus, and another center is in this at this point. So sun may be one of these at one of these focus. and this planet revolving in this elliptical path like this. Okay. Now Kepler's second law, or law of equal areas. The radius vector drawn from the Sun to any planet sweep equal areas in equal interval of time. This law is called as law of area. The areal velocity of the radius vector is constant. That means a line joined to the planet and Sun, that is the radius of the orbit of the planet, sweep equal area in equal interval of time. Suppose look this activity. Now planet sweep this area, then this area, this area. The area of all these bands are equal. That means the planet sweep this area in equal interval of time. म्हणजे ग्रह सूर्याभोवती फिरताना ग्रह आणि सूर्य यांना जोडणारी सरळ रेषा समान कालावधीत, समजा या ठिकाणी 1 तासामध्ये एवढा एरिया त्यांनी कव्हर केला असेल, लाल त्रिकोणाने दाखवले. जेव्हा तो सूर्याच्या जवळ जाईल तेव्हा देखील 1 तासात तो इथं दाखवलेल्या ह्या एरिया, हा एवढा एरिया स्वीप करतो, म्हणजे तो त्यावरून तो जातो. त्याच्यानंतर या पुढलं या ठिकाणी जो दाखवलेला आहे तिथं देखील त्याने स्वीप केलेला एरिया दिसायला जरी ते भिन्न दिसले आपल्याला एरिया, तरी पण त्याचा एरिया मात्र सेम असणार आहे. ज्यावेळेस प्लॅनेट सूर्यापासून सनपासून खूप दूर असतो त्यावेळेस हा एरिया जो असतो तो सेम तेवढाच असतो, फक्त त्याचं स्पीड थोडं कमी झालेलं आपल्याला दिसून येईल. Kepler's third law, or law of periods. The square of period of revolution of the planet around the Sun is directly proportional to the cube of semi-major axis of the elliptical orbit. Simple. We can say Kepler's third law states that the square of period of revolution of a planet is directly proportional to the cube of radius of the orbit of the planet. In this equation, this law we can show here. T square is directly proportional to r cube. T square is the time period of revolution of the planet. That means the time required to complete one revolution around the Sun is called as period of planet, and it is denoted by capital T. According to this law, when the planet is closest to the Sun, its speed is maximum, and when it is farthest from the Sun, its speed is minimum. That means when planet revolving along the elliptical path, as shown in the previous slide, when planet is near to the Sun, at that time radius of the orbit is less, and the time period is small. Time period is small, that means velocity is maximum. While planet is apart, farthest from the Sun, at that time the radius is increased, so the time period increases. Time period increases means velocity decreases. Speed of the planet decreases when planet is away from the Sun. So this is about the three laws of planetary motion stated by Kepler. Now, difference between gravitational constant capital G and gravitational acceleration small g. This is gravitational constant capital G. In Newton's law of gravitation we defined it, and the gravitational acceleration, you know, the acceleration produced in an object due to the gravitational force of Earth is called as gravitational acceleration. What is the difference in between them? First difference, gravitational constant G is the universal constant, where G, small g, gravitational acceleration is due to gravity, and it is not universal constant. It changes with place to place. Then value of gravitational constant in the universe, 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. While the value of gravitational acceleration on Earth only, approximately 9.8 meter per second square. It varies from one place to another on the Earth also. The value of gravitational acceleration G at the equator is near about 9.78, while at the polar region it is approximately 9.83 meter per second square. That means the value of G is variable, not a constant. Then last difference, constant throughout the universe. The gravitational constant is constant throughout the universe. विश्वात कुठेही गेला, कोणत्याही दोन वस्तू असल्या तरी देखील ह्या ग्रॅव्हिटेशनल कॉन्स्टंटची व्हॅल्यू चेंज होत नाही, ती हीच कायम राहते. Whereas gravitational acceleration changes every place on a planet. Example, on the moon, the value of G is 1/6 of the Earth. Also, it is changes with height, altitude, depth. So, now next, relation between gravitational constant G and small g. Suppose the mass of the Earth is capital M and small m is the mass of an object on the surface of the Earth, and g is the acceleration due to gravity on the Earth's surface, and r is the radius of Earth. From Newton's law of gravitation we can write the gravitational force as Gm here, Gm into m upon r square. This is the gravitational force. And the weight of object, in 9th standard you define the weight of object, and the formula of weight equal to mg. Weight means the gravitational force acting on the body. This force, gravitational force, that means weight, and this gravitational force, Earth and the object, in between Earth and object, that both are same. Since we can write they as shown in this equation. Then by neglecting a small m on left LHS and RHS, then we get the value of gravitational acceleration as g equal to gm upon r square. In this equation, the gravitational acceleration g depends upon the mass of Earth. Capital M is the mass of Earth, r is the radius of Earth, and g is universal constant. Generally on the Earth, the radius of Earth we assume it is a constant. G is the gravitational universal constant, and mass of Earth remains constant. So on Earth, the value of G is constant as 9.8 meter per second square. According to the radius at different places, it shows little changes, but generally we can say the value of gravitational acceleration on Earth g is 9.8 meter per second square. From this equation, the value of gravitational acceleration not depend on the mass of body as shown in figure. This is the Earth having mass capital M, and this is the object of mass small m. From this equation, the object on the Earth of any mass is not related to the gravitational acceleration. That means the gravitational acceleration produced in any object of any mass is same at that place. Then variation of g with altitude. Altitude means height. At a height h from the surface of Earth, as shown here, this is the Earth's surface and the object is at height h. The acceleration due to gravity assumed as gh at height h. Weight of the object equal to gravitational force, we see in previous slide. So the mgh equal to gm upon r plus h square. Hence the gravitational acceleration of the object at height h is gh equal to gm upon r plus h square. If the height increased, then this value goes on decreasing. From this equation, we can say the value of gravitational acceleration goes on decreasing with increasing height from the Earth's surface. Then the relation between the gravitational acceleration of any height and at Earth's surface. gh equal to gm upon r plus h square as shown in the above equation. If we divide it by g, then we get gh upon g, value of g equal to gm upon r square. In previous slide we see here g equal to gm upon r square and gh equal to gm upon r plus h square. If we take the ratio of these two equations, then we get gh upon g, then capital M, capital G, both are same in the equation, they get cancelled. Then remaining part of the RHS is r square upon r plus h square. So gh upon g equal to, by simplifying this equation, last we get gh equal to g into bracket 1 minus 2h upon r. Also from this equation, the value of gravitational acceleration at height h from the Earth's surface goes on decreased with height. Then variation of g with the height g, we get the equation in previous slide, gh equal to g into bracket r upon r plus h square. The g is independent of the mass of object. Any object of any mass, the value of g does not depend on that mass. It is related to the radius of Earth and height from the surface as shown in this equation. Thus g is independent of the mass of the object. From this equation it is clear that the acceleration due to gravity decreases as altitude, that means height, of the body from the Earth's surface increases. Then variation of gravitational acceleration g due to depth. The acceleration due to gravity on the surface of the Earth is given by equation g equal to gm upon r square. What is g? G is the gravitational acceleration and the capital G is the gravitational constant, and this capital M is the mass of Earth and r is the radius of Earth. Consider the Earth as a sphere of density rho. From the equation formula of density rho equal to mass upon volume. Then we get from this formula mass equal to volume into density by simplifying this equation. Then mass equal to volume of the Earth. Earth is a sphere and we know the volume of sphere, formula of the volume of sphere equal to 4 by 3 pi r square. R is the radius of Earth, pi r cube, into density rho. Then we get the acceleration, mass g equal to, from the force equation, F equal to mg. In this equation, if we put the value of mass 4 by 3 equal to pi r cube into rho, then we get the value of g. I write here g equal to g into 1 by 3 pi square rho upon r square, pi r cube rho upon r square. R square is cancelled from r cube, then only r is remains on the numerator. Then we get the equation g equal to minus 4 by 3 pi r rho into capital G. So this is about the gravitational acceleration. Now the assignment for you: obtain an expression or value for the acceleration due to gravity at the equator. Then second, obtain an expression value for the acceleration due to gravity at the poles. Then variation of g due to depth. Consider a point P at the depth d below the surface of the Earth. At this point, let the acceleration due to gravity will be gt. D represent the depth. Distance of point P from center of Earth is r minus d. जेवढी डेप्थ वाढेल तेवढी रेडियस कमी होईल, म्हणून the distance of point P at the depth d from the center of Earth is r minus d. The acceleration due to gravity at that point P due to sphere of radius r minus d will be given by this equation gd equal to gm square upon r minus d square, as we studied. Here m is the mass of the inner solid of Earth's sphere of radius r minus d, and it is goes on decreasing with increasing depth. the value of mass of Earth that exerting gravitational force goes on decreasing with increasing depth, because the radius r minus d decreases with depth. So consider the point P at the depth d below the surface of the Earth. Then we get the equation: distance of point P from the center of Earth is r minus d. Then again, by the equation of density, we get mass equal to volume into density. Suppose the mass of the Earth that exerting gravitational force at depth d is m dash. Then we get m dash equal to 4 by 3 pi r minus d cube into rho. Then gd equal to, by simplifying this, lastly we get the equation gd equal to capital G into 4 by 3 pi r square, 4 by 3 pi into bracket r minus d into rho. From this equation, with increasing depth, the value of G goes on decreasing. So this is about the gravitational acceleration. We see the next part of the chapter in next video. Thank you.